All right, thanks. So this is based on joint work with Keith Levin and Elizabeth Levina in the statistics department here. So, sorry, these talks are slightly recycled. So thank you for inviting me. I think this is informal. So yeah. So the two papers this is based off of is one which is in the Journal of Random Matrix Theory and Applications, and another which is posted and submitted. Okay, I'm doing it Beamer, but I'm using a Chromium tab, so this might be slightly interesting. Okay, so whoa, that went up ahead. Okay, so let's go ahead and do it this way. All right, thanks for this. So let me sort of start by talking about what kind of matrices we're obtaining in the context of statistics. I'm going to give several examples, but the common feature of all these matrices is that they're a collection of positive semi-definite matrices. Okay, so in the first case and the one that our lab and we actually had data sets of were a bunch of fMRI scans. Okay, so each of these x1 through xn, capital N is the number of people, p the number of rows is how many points the brain has been discretized in. And the sequence n sub 1 through n sub n is just how many snapshots in time you took of the subject's brain. Okay, so this is what we mean by time series, just a stochastic process, but statisticians call it a time series. So if you were to compute the autocorrelation of this xi, so I'll explain what that means, but I can say it in words. Just take x1, multiply it by its transpose, so x1, x1 transpose, and then divide by the number of samples, n1. That's called the autocorrelation. When you do that, you get a positive semi-definite matrix. Okay, so that's just from linear algebra fact. Once what we would actually work with these autocorrelation matrices, because they're very noisy, is we would actually turn them into graphs. I don't know much neuroscience. The reason that they really turn these things into graphs is they have this notion of some connectome and they're trying to figure out different sites of the brain, how they're connected. But for me as a mathematician, what I know is this thresholding concept is whenever the matrix entry is above a certain value, you set it to 1. And if it's below it, it's 0. So when people say I thresholded something, that's what they mean. They do an indicator. Or they kept the value, like, so one way of doing it is just put 1 or 0, or one way is keep that value and then any value above a certain amount, just 0 it. So two different notions of thresholding, it's just a concept. Then you can take these matrices and you can compute their graph Laplacians. So you may have heard of the Laplacian where you do the degree. So the diagonal matrix is the degree of each node in this adjacency matrix. You multiply it on both sides by d to the minus 1/2, and that's one Laplacian. But there is another Laplacian that's positive semi-definite as well. But most often than not, like the setting that you get positive semi-definite matrices in statistics are sample covariance matrices. So now you have a collection of vectors, independent IID. This looks a lot like the time series one. But in the time series case, the observations may be correlated along the columns. Here, each column you should think of as a separate snapshot, just an independent copy of a p-dimensional vector. Okay, so each of these x1 through xn's are IID matrices, and you can compute their sample covariance by xi transpose over some ni. So it just so happens to be the same as the autocorrelation matrix. And I know this is a lot of terminology, and we're not necessarily familiar with statistics. Anybody have any questions right now?
So far you are considering unique distribution on the IID distribution.
Yeah, so so I'm not putting a distribution yet in the beginning, because the trouble is that at least with the autocorrelation one, this is a point where people can take a lot of objections, right? If you put a stationary stochastic process on the brain, people call BS very quickly. Sorry for the language, but it's not something one should do. A priori, if you just had data points, you can just compute these concepts. So let's just say this is deterministic for now. It's simply an observation that data comes in this form. But the distribution, these are where there's controversies. So for example, for an adjacency matrix, people use the stochastic block model, which is Erdős-Rényi, but there's inhomogeneous probabilities in various blocks. That people can say that's ridiculous, right? Because the brane, it's not independent edges, but people do math with it. So this is sort of more to sort of avoid the distribution just yet, but I will put a distribution later on and discuss that. Any other questions? Okay, if not, I'll continue. So one observation is that if these different collection of vectors are independent, identically distributed, then this separation into capital N vectors is completely, artificial, right? Like if someone said, I'm going to do my data, but I happen to label them 1 through n, but I don't think they're different, just merge all the columns together and make one big massive matrix, right? I mean, it makes sense, right? Like nobody, if people didn't even know the distribution, they just say, like, look at it all at once. I'm going to say this as a side comment because it will play a role later, but we may still separate just because computationally it's not feasible to analyze one big matrix on one computer. Okay. So I mentioned positive definiteness, but why am I doing that? And what is it that we're actually trying to answer fairly often? Often what you want about a matrix, if you put any distribution, is its expectation. Okay. That just happens to be what most models, the parameter you're trying to estimate, is related to the expectation of these individual matrices. So for example, if you have graph Laplacians and they were, say, the stochastic block model, then the expectation of that matrices leading eigenvectors contains info on community structures. So think about if you had a hidden clique, the adjacency matrix would have like a block of 1, 1 transpose, like a bunch of ones on the off diagonals in a block. When their sample covariance is the leading eigenvectors of the expectation is the signal we wish to recover, right? So that's another example of this. So often what people do is to estimate things, and this is from standard probability theory, the first thing you learn is law of large numbers. If you take the arithmetic mean of a bunch of independent observations, right, then it'll converge at a very fast rate when they're scalars to the true expectation, right? So this true expectation. Okay, but in the more general case, in the more general setting, in matrix land, like maybe we were thinking this wasn't necessarily, there are other alternative means to consider. Now, why would we think this? There was actually a paper we were looking at. And this is a paper due to Armin Schwartzman. I can give a reference at the end. And so the context is diffusion tensor imaging. Okay. So what you do is you take the brane into these cells, and the lingo for them is voxels. And you map each voxel to a 3x3 water diffusion matrix. So, and that's because of how things are measured. So I know this is getting very applied, but don't worry, we'll get back into random matrix land and free probability soon. But I wanted to sort of motivate that there are cases in statistics where changing your mean is being considered. There's caveats, but what can you do? So what Armin did was he put a density on these matrices, and what he did was that he started with a 3x3 matrix, and he considered its vectorized part. It's symmetric, so I only need diagonals, x11, x22, x33, and then 3 off diagonals, x12, x13, x23. And then this vector of everything on the off diagonal and the diagonal, assume it's distributed according to a normal, so that's what this means, mean mu, variance sigma, s, sorry. So when you're applying this density in statistics, we need to discover what this mu and this s are. So we want to estimate what those parameters are to figure out, to make predictions about things about the subject. So to get a positive definite matrix, what he did was he exponentiated this matrices. And then he called this a log Euclidean log normal distribution. Okay. So the way that then what ends up happening is that if you assume that they're distributed according to this log Euclidean log normal matrices, the MLE, which is called the maximum likelihood estimator, to recover the expectation and the covariance of this vector, are these two. So let me explain. Maximum likelihood estimator is literally this. If I got this sample, what choice of the parameters M and S maximize the probability of W1 through Wn? So it's argmax the density over M sub S. That's what M hat is, and that's what S hat is. Okay. Notice we took the log Euclidean average of these matrices. Okay. So why do statisticians care about the MLE? It has some nice convergence properties as the number of samples goes to infinity, and key thing, the dimension of the matrices remains fixed. People consider all sorts of different estimators, but there's a lot of theory that if you look in these mathematical statistics books, they prove theorems about them. That doesn't mean this is a good thing to do. So I'll talk about that right now. So as you can see, the sample covariance is also some other variant of the sample covariance, but here is what I want to emphasize. It's the mean. So here's a picture of what he did. And this is just so I don't give you any sort of impressions that like this is definitely going to be useful in practice, any of the considerations we talk about, and later on I'll explain even more. What these three photos are, I didn't really do a good job with this caption, but there was 34 diffusion tensor images, and 20 of them were boys and 14 of them were girls. Okay. These three axes were flow lines, so that's what the anisotropy thing is. I don't fully know fluid dynamics, but it's like some flow in each of these directions. That's what that 3×3 tensor is supposed to represent. And what these graph is it's the results of what's called a two-sample test. So they were trying to test if boys' and girls' brains are different. And the results of the colors represented the different p-values. So I give you the caption for the figure. It explains more in detail. But they were very similar. I'm only talking about these two. There was like a third, like Riemannian geometry he considered, but this is computed very quickly numerically. This one's maybe a little bit faster. Oh, no, a little bit slower. No, like a little bit slower. And this one is like a day. So this is 1 second, 2 seconds, so on. So it's not like it's unreasonable to ask about these questions, and people are considering them in the context of real world questions. Okay. Now, we were looking at this and we're saying, okay, this figure was actually not promising. It was basically saying there's no reason to worry about it because the difference between these wasn't that high, but the computational cost of these difference wasn't really worth it compared to the Euclidean average, at least for this density. Okay, but each of those matrices is 3×3, and the sample size at each cell was 34. Okay. So in random matrix theory now, we consider these high dimensional problems where the dimension of the data, P, is proportional to the number of observations. And this is the asymptotic regime. The limit of this ratio is going to some point gamma. Okay. And if you had PSD WI, the concrete question we want to ask is, in this particular regime of P over N going to gamma, is there a matrix mean that improves on this on estimating the expectation in a matrix norm? And then we'd specify which norm. The leading eigenvector of the expectation. And can we quantify the effect? So those were the questions we set out to ask. Okay. So here's a concrete model. I have a sequence of 1 through capital N. So this will be the density I consider from now on. Just a bunch of Gaussians. Okay. I have capital N, identical rectangular IID normal 0 sigma Gaussian. Okay. So it's not the time series thing. It's not any of those other things. Let's just start with the simple case, even though we know that there's a lot of things that people care about, and we would like to sort of see if this has any implication. And now you get these Wishart distributed matrices. This is this xi transpose over little n. And this is the so-called Wishart distribution with parameters p and n, and I should say capital sigma. Okay. So there's some statistical theory significance of the arithmetic mean, which is that it's what's called a sufficient statistic. So I'll explain what that means. So if I take the density and I split it into a conditional density on this random variable times the density of the random variable, then the density of f sub a, of little a, factors out. There's no more dependence on sigma. So I know that sounds subtle, that's a little bit strange sounding. So conditional on a, the dependence of the density on sigma is entirely determined by its conditional density on a. That's what they mean by sufficient. It's a concept due to Hallmush and I think Savage was the co-author, but it's a fairly fundamental one in mathematical statistics. I'll come back to this. That sort of conditional fact is kind of important. So this is why people are really almost ideological about A being the best thing you can do in some sense. And again, we do the high dimensional regime, in the limit that P over n goes to gamma. But we keep it between 0 and 1 because the matrix mean that I want to compare it with is the harmonic mean. In a sec, I'll get to that. But first, let me introduce one more parameter. So remember how I said each of the columns of these data are IID, so you might as well merge them? Well, that's what this is. So little n times capital N is the total number of data. And if you compute the corresponding aspect ratio of that big matrix, you get capital gamma as the limit of P over the total data. Okay? So we call this aspect ratio, P over N. So the aspect ratio of the total data asymptotically is capital gamma. The aspect ratio of each individual matrix is little gamma. Okay? So it just so happens that if you were to think about it, this matrix A is, this arithmetic mean is in fact merge all the columns of the xi's into one big matrix and take that times its transpose. So in fact, it's almost like I should just be writing a big W instead of writing it this way, but you know, it's actually going to be fairly fundamental later on why I'm doing that. So okay, so this was an intro to random matrix theory. These slides were also targeted at statisticians at the time, but since I was told that this group might study more integrable probability rather than RMT all the time, I decided to sort of mention why it's relevant to statistics. So RMT often studies the eigenvalue distribution of random matrices. And okay, like I'll just kind of go through this fast. The eigenvalues are like a collection of random points. So you can consider statistics such as the Frobenius norm. So treat the matrix as a Euclidean point and take its L2 norm. And that's actually just a linear statistic of the eigenvalues. So you can actually estimate the error of stuff by knowing a linear statistic. So if you were trying to do regression on a matrix and you had a Frobenius norm error, so that's like figure out the best L2 approximation of something. If you knew something about the eigenvalue distribution, you would just know it. But that could be overkill, So in RMT, we treat these as point processes and we study the limit, in which case this right-hand side is the integral of some random measure. Okay. And that's why I talk about this CDF, because essentially the CDF is what if you integrate by parts, this lambda j integrate against the CDF, you can write the Frobenius norm in terms of that. And here's a histogram of all these eigenvalues. And this is the arithmetic mean A with 500 samples and 2,000 total points compared to the theoretical limit, which is called the Marchenko Pester distribution. So first, I want to note that, actually now I remember why I put this picture. So these Wisharts, so just to remind you, I took a bunch of Wishart matrices, or one big Wishart matrix of this aspect ratio, and I histogrammed its eigenvalues, and they're from the identity matrix. So sigma is the identity, so I have a bunch of normal, zero, identity. Now, if this estimate of A was accurate, everything would be piled up at 1, right? Because all the eigenvalues of the covariance matrix are the identity. All the eigenvalues of the identity matrix are 1. There we go. But in fact, you see this smearing, and that's due to this high dimensional regime. So what statisticians like to say is the matrix is inconsistent. That is, it doesn't converge in the limit to what its expectation is or what it's meant to estimate. Okay? So they often say an estimator is inconsistent if it's not converging to what it's supposed to. So this is the fundamental Marchenko Pester Law. So when the theoretical limit I was alluding to is the following. If I have a random Wishart matrix and I look at its CDF, it converges to the integral of the following distribution, which is a square root one, with these parameters, gamma plus minus being this. Okay. Now, as a direct consequence, this Frobenius norm error is, if you integrate x minus 1 squared against this, you get gamma, which is not 0. So to just drive home that this matrix is inconsistent, I do this integral. But moreover, a more powerful result is the operator norm, the largest singular value of this matrix, is gamma plus 2 root gamma. And the trick with that is just take the density, just take the eigenvalues, subtract 1, take the biggest eigenvalue of 1 plus root gamma squared minus 1 in absolute value, and 1 minus root gamma squared minus 1, and it's just this, for any gamma between 0 and a half. So then we said, okay, we know everything we need to because random matrices like absolutely killed this matrix in terms of every possible result that you could think of, except for some really fine properties, is pretty much known. So we have a baseline to compare to, and now we're comparing it to the harmonic mean of these matrices. Okay. So it's a clear function of the random matrices, and we know some things about this. So why did we pick it? Because there's this thing called the arithmetic and harmonic mean inequality, AMHM inequality. And this generalizes the classic one of scalars. Okay. So why would we do this? Because I bias the eigenvalues towards 0. So statisticians, okay, so if you have like a sufficient statistic, I think this is right, but like I might be saying the terms wrong because I'm mostly a probabilist. But when you bias an estimator somehow to 0 compared to some other one, sometimes, and you get an improved estimator, they call this a shrinkage phenomenon because you bias it towards something. Okay. So what we noticed was that let's graph this thing, and they look very similar, but look very carefully at the edge. Okay, so the lowest eigenvalue of the harmonic mean is closer to 0, but the largest one is at 1.8 or something, whereas for the arithmetic mean, it's like 2.25. So when you compute the operator norm error of H, it's actually smaller than that of A. Okay, and moreover, nobody had actually analyzed up until our work the eigenvalue distribution of this sort of matrix mean. And what we did in the first paper was we used free probability theory to compute the following distributional result. Okay, that is, the CDF goes to something very similar, but now it depends on this capital N parameter. So now remember, I said that A doesn't see the capital N parameter, the number of little matrices, submatrices that I union together to make one big XX transpose. But weirdly enough, H does. And I'm sorry, did I mention that, okay, H is W1 inverse plus W, just to sort of make it clear. That's this H. So there are capital N matrices that are be harmonically averaged, and this capital N is appearing here. Okay. And this constraint is to ensure that you don't split them to make those matrices non-invertible, right? So I'm parameterizing in terms of capital gamma instead of little gamma that usually people do, but that distinction is not existing in the arithmetic mean. It exists in the harmonic mean, however. Okay. Now, if we actually also proved in that paper that we have the following almost sure convergence of the operator norm. Okay, and again, you do the same thing. Subtract 1, take the biggest absolute value. That's your predicted thing, but the actual operator norm result was kind of delicate because each of those matrices you have to worry about its smallest singular value, and that's like somewhat, sensitive. But there are so many powerful results due to, say, Rudelson, Vershinen, Tao, and Gu, and all these people that like we had everything we needed to prove this. Okay, for complex Wishart. We had some limit issues with some other results to generalize, but and they were just purely technical. I think this generalizes to anything with sub-Gaussian entries or something. They're just either proof from scratch or just cite something. So then I'll talk about the Frobenius norm in a sec, but so all of this is for the identity covariance. So all the Gaussian vectors are identity. But what about general population? So when people talk about the parameter sigma, they call it the population. This is a way to make friends with statisticians. How much am I doing on time? Okay, I'm still only halfway through. Okay. So what about the general population? Well, what's interesting is it's just purely matrix multiplication to give you a general Wishart. And that's by just looking at the Gaussian density. So if you were to multiply by root sigma of this positive definite matrix on both sides, you get a Wishart with another covariance. Okay, so what we did is that we derived a characterization of the spectrum in the same paper for a general covariance sigma. And what we proved was that if you know this result for the operator norm is smaller, then in fact it follows that for a general covariance you're smaller. So in fact, even though we're proving all these very fine results for the identity case, we can also get things for general covariance. But to circle back, what is this operator norm calculation I'm doing and what does it mean? And this is something that's kind of quite interesting. So for the identity covariance, when capital N equals 2, so when you split your matrices in exactly 2 halves, you always, with probability 1, improve asymptotically your operator norm estimator from the arithmetic mean. Just with probability 1, asymptotically. And because of this submultiplicativity argument, you actually get it for some general class of matrices depending on the condition number. But notice that the whole thing was that H depends on how you split the matrices, but A does not. So that's why we were able to improve it, because we could select it, minimize the left, but we could do nothing to the A to improve it as it was. But what is the meaning of this N when you have the Xi? So remember this comment I made earlier about, okay, it's artificial if the data is IID to split it into submatrices? Well, now it's not arbitrary if you're computing H. Like there's no, like once you invert one of the submatrices, Xi transpose, you put meaning onto that submatrix. But what I'm saying is that if you arbitrarily split it, you don't even look at it. You split it in 2. In fact, you shouldn't look at it because that would make it not IID W1, W2, right? Arbitrarily splitting in 2 always improves it. So people were really shocked when we said this because they said, well, A is sufficient. A is this amazing thing. How could you do this and always get an improvement? Right? So they actually didn't believe me. So, and yeah, so just driving home that we could choose N. And it's always best to choose a split of 2 is what the result says. Okay, so then let me just sort of state it from the beginning as a data splitting possible application. But you'll see that this can't be used in practice. Well, first off, you would never do this in practice because inverting a matrix is a horrible thing to do numerically. So other people are saying that's just ridiculous. Don't ever invert a matrix, even if it is good. So suppose I have a subset of p-dimensional IID Gaussians with population covariance sigma, and we have this asymptotic. P over the total number of points is going to some point gamma in between 0 and 1/2. Then, if I partition the data set into 2 equal size vectors, I have this lim sup result if the condition number is small. So now it's a general data set, and I have this statement, which looks weird, which looks kind of like, you know, for a statistician, this is kind of freaky. So now let me go back to why do we care so much about operator norm? Okay, well, so there's this result in perturbation theory called the Davis-Kahan Inequality. So remember I said one of the reasons people estimate the mean is because the original parameter, sigma, its leading eigenvector is something we want to estimate closely. And this inequality allows one to connect those 2 concepts. So the leading eigenvector of any sigma hat minus the leading eigenvector of the truth is bounded by this. And lambda 1 and lambda 2 are the first eigenvalue and the second eigenvalue. So they call this denominator the Eigen Gap. Okay. So intuitively, if this is small, these should be close. Okay. So, and in fact, it's often used to argue eigenvectors can be recovered as these get small. And in finite dimensions, where the dimension of the data is small, often this just goes to 0 as the number of samples go to infinity. Okay. So here's that line of reasoning. Okay, so take a symmetric matrix. I know its operator norm is nested with this Frobenius norm. So all I got to do is control one of those norms. I know the operator norm is going to 0 because P is fixed, right? So anything that's easy, and Frobenius norm is really easy because it's just L2 norm of a bunch of things. So if one of these norms goes to 0, then I know my eigenvectors are converging to what they should be. So this is just stating more concretely what I said. But as P goes to infinity, these norms are order 1. So when M is the Wishart, or when M is A or H, so I guess M is I'm sigma hat minus sigma, which is A minus identity, or H minus identity, I should say. This thing is O of 1, and this upper bound, this bound is also growing to infinity. So basically this inequality means nothing in this regime, because 1 over P, A hat minus A is going to 0. So just to sort of explain, so the Frobenius norm error of this H is going to gamma, which means in the previous slide, if I need to multiply by P, and I'm actually asymptotically growing if I use the first operator norm inequality. Okay, so sorry, I went a little fast there. So let me just go up to sort of clarify. So what I'm trying to say here is that if I tried to argue that from the operator norm, the Frobenius norm error was going to 0, well, I know the operator norm error is O of 1, and then when I use this inequality, the root P makes it go to infinity. On the other hand, because 1 over P times the operator norm error of A or H is going to O of 1, then in fact, the actual Frobenius norm is going to infinity, so I can't argue anything about the operator norm. And then I can't say anything about the eigenvectors by using Davis-Kahan if I don't know if this estimate is getting everything is bounded by infinity. Okay, so, but one more interesting result is that in fact, the Frobenius norm error and the error of the arithmetic mean, both the harmonic mean and the arithmetic mean are actually the same, which was also something I could freak people out about. You kept the operator, you made the operator norm smaller, but you made the Frobenius norm the same, which gives, it's counterintuitive, especially if you want to say anything about estimating anything, that like, okay, here's this estimate that improves your operator norm error, doesn't change your Frobenius norm error. What does that mean about eigenvectors? Right? Like, it's hard to say, right? So other kind of ways that people have dealt with these kind of estimation bias. So the phenomenon I'm talking about improving upon the arithmetic mean isn't new at all. In fact, there are very famous papers where the way they improve on it is taking a convex combination in the cone of the positive definite matrices with one A and one target matrix. And there's like an art to choosing this lambda and 1 minus lambda, and there's some theorems that minimize specifically the Frobenius norm. So most shrinkage estimators are focused on making your Frobenius norm error as small as possible. Ours made the operator norm error smaller and kept the Frobenius norm error the same, right? So what does that mean? What will that do? Well, we started considering a case where there was actually eigenvectors to look at. So what we did was we said, okay, let's consider a spiked covariance model where sigma is identity plus theta VB transpose. And let's consider okay, just to kind of state some clear facts, like there's one eigenvalue at 1 plus theta, and the rest are at 1. The Davis-Kahan inequality gives the following upper bound as a result. So if the Eigen Gap is just going to be theta, so put theta in the denominator, and whatever your estimate sigma hat is, it's just sigma hat minus sigma op. Okay, so plugging in identity plus theta VB transpose. So we have a concrete thing that we need to compute the limit of on the right-hand side, and a concrete thing on the left-hand side that we're concerned with. So what that suggests is, without any sort of true proof, even though we know things are going to be in the operator norm sense, if you were to just operate on a heuristic level, you would say that, well, since H's operator norm is smaller than A's, this should suggest, even though it's not a proof, and even though the inequalities may not be comparable, that the leading eigenvector of H should be closer to the truth than the leading eigenvector of A. Okay, but let's see if that's true. So what the baseline result, and this is the very famous BBP transition, that if you have a spiked random matrix model for the arithmetic mean, the leading eigenvector of the arithmetic mean is orthogonal if your theta is below some critical value. So if I'm below a certain value, my leading eigenvalue stays at the same point. It's not changed. There's no Eigen Gap. And my signal is asymptotically orthogonal to the truth. Because it's a high-dimensional space, there's lots of places for it to be. This is a one-dimensional subspace. So it's basically my leading eigenvector is just noise. But if I have a big enough signal strength, theta, so my spiked model is identity plus theta VB transpose, then the leading eigenvalue escapes, there is an Eigen Gap. So gamma plus is the right edge of the Marchenko Pester, and this is the leading eigenvalue of this spiked model. And I have some correlation. So it lands in some cone. So it's not 1, that would mean it's aligned, but rather it's something slightly smaller than 1, or depending on theta and stuff. Okay. And this critical value is root gamma. So root aspect ratio is these results. So this is a very famous set of results, Bike, Paul, Hoyle, Rattray, and Nadler, and so on. And basically, it's high-dimensional signal recovery. Okay, and by the way, if your target matrix, so a lot of, sorry to scroll up so fast, but in this model, a lot of people just took the target matrix to be the identity, right? So any sort of B being the identity, being your target matrix, is not going to change the eigenvectors. It's just a linear combination. So even if you made the Frobenius smaller, you didn't do anything to improve the leading eigenvector recovery by doing so. So all these results about the Bike case is actually relevant then, because even if I put lambda identity A plus 1 minus lambda identity, I'm still getting this result applying to the leading eigenvector recovery. So even though I'm improving this Frobenius norm error, those shrinkage estimators aren't going to really help you if you didn't change the eigenvectors at all. But now the question is okay, we found one that improved the arithmetic norm, the operator norm recovery. So what about the harmonic mean? Okay, so we take n equals to 2 because that's when our operator norm error is the smallest. Well, there's also a critical value of this phase transition regime. And below it, you had the same style of result as Bike and all these other people, and Johnstone. And above a certain amount, you get a different formula, okay, which we have explicit calculations for. Okay, so I don't expect you to do this algebra in your head, but first, let's look at the phase transition value. So before, for A, it was easy to remember. It was just root gamma, but here, this is not promising. It's root gamma over 1 minus gamma, which is bigger. So what that means is I need a much bigger threshold before H recovers anything about the leading eigenvector, because below it, I'm orthogonal. So that means A is still better, which is kind of disappointing to us. Yeah, so this is the detectability threshold for H estimator. And in fact, for every of those gammas, you're actually less correlated than A. So in spite of this eigenvector recovery and this intuition, I'm actually doing worse off by doing this, okay? Which really disappointing. And like you could pick everything so that you're even guaranteed. So remember, we only had their operator norm results for the identity, but now we did identity plus theta VB transpose. Well, okay, this is just to do our sanity check that in fact, I picked theta small enough so my submultiplicativity argument guarantees me that H is in fact improving A, even though I don't have a technical theorem for it. And this is simultaneously true. Okay. So let's just sort of, I'll say this all very slowly. Okay. So first thing is, H is not going to recover if your signal strength is weaker. A is more likely to recover. Second, even when it does recover, I'm doing worse. Okay, I'm less aligned. This should be closer to 1, and so on. Next, I can even find a collection of thetas and gammas for which this regime is true. So my Davis-Kahan intuition would suggest this should be bigger, but in fact, this leading eigenvector of H is orthogonal. So in fact, the left-hand side is 0, but if I use my inequality, then I would assume that it's better. So now, why am I really driving this home? I'm sure, like, for those of you who've done like linear algebra and perturbation theory, you know that like Davis-Kahan and has like deterministic counterexamples. But one of the problems with asymptotic theory and statistics is fairly often they'll tweak the asymptotic and they'll make the operator norm go to 0 at a certain rate. And they'll say, look, we're consistent, right? But P and N are finite and big, right? That's why I look at the regime P over N going to a constant. So often they'll state that I'm doing better in operator norm error, and then they'll state that as if people should just then trust Davis-Kahan means I'm doing better in general. But if all you do is change one line in their asymptotic, then you're not guaranteed that things are going to 0. You're now guaranteeing that things are O of 1, maybe. In which case, I have an O of 1 improvement, but I don't know whether my eigenvector contains any signal at all, which is alarming, right? Like this is like the asymptotic theory for this one suggests it's really bad, and the asymptotic theory for this one suggests it's pretty good, or better at least than that. So that's kind of the high level of, at the very least, when we do this positive semi-definite estimation and leading eigenvector stuff, we should be really careful about our overemphasis on the operator norm error and our classic sort of analysis. And okay, so this was my sort of plug that the choice of matrix means matter. And yeah, we kept the Frobenius norm error the same. I think I was sort of making an error. Okay, sorry about that. I overdid it. So okay, but one thing that was crazy that we got surprised by towards the end, even though there was some, slightly disappointing results, was that we were actually able to compute the Rao-Blackwell improvement of this H. So remember how I said this sufficient statistic of this model is the arithmetic mean? Well, there's this theorem called the Rao-Blackwell inequality, which states that if I compute this conditional expectation, I improve my estimation error of the operator norm in L1. So it's just Jensen's inequality, really, and that comment that the density factors out. So you use Jensen's inequality under the integral. The point is that this conditional expectation minus the true parameter in operator norm is going to be smaller than H asymptotically. We can guarantee that. And this is the one kind of integral probability thing, is that we could actually compute this integral. It's a beta integral, specifically only in the Gaussian case. And the trick is note that there's this matrix identity. H is 2A minus this W1, A inverse W1 over 2, minus W2, A inverse W2 over 2. And now that's, if we computed the Jacobian from A to H, it's triangular. Oh, wait, I'm sorry. W1 given H, I think it was. But anyway, so you get a beta integral in a matrix variant beta integral, which was actually computed. So, that's right. So compute the density of W1 conditional on A, and you get a beta distribution. And then this, if conditioning on A, if you integrate this was done in Konna, 1988, you get this, which is a scalar multiple of A. So this is back into that category of shrinkage estimators, right? Where the target matrix is now 0. Okay, so in fact, if you wanted to guarantee an improvement, you can go back to this class of estimators, which I don't think anybody ever had an interpretation of this convex combination as some conditional expectation of some mean on the positive definite cone. But we actually feel like we fully understood the phenomenon from beginning to end of what was going on and what can improve it, even though at first it was very strange. So the rest is just some simulations of how it behaves. So it's the relative norm error, and let's just leave it at that. Call it a day. Anyway, so I'll go ahead and stop sharing. If there are any questions, feel free to ask.
Okay, thank you very much. Let's see if there are some questions.
Anas, I think it is.
Yes, please just speak on.
Yes, sorry. So I work in random matrix theory, but my probability theory isn't that strong, which is why I'm coming to these seminars. So I have a few questions.
Shoot.
So can I just quickly go through the idea here? The idea is, or your intended application is, you have these, I guess, measurements, like an actual real life, I don't know, brain scan measurements or population, and you want to understand the covariance matrix, and your belief is if you sum up the matrices, that's the arithmetic mean, you should recover, right? So you then say, okay, let's just assume our measurements are random. So our expected mean should be the identity, right?
Right.
If you actually had a proper collection of data and you knew the mean, that arithmetic mean and the harmonic mean should converge to the true mean, right?
Right.
Right. So I guess what's happening here is that you're taking a sum of random variables and you're talking about like how different that is to what would happen if you had actual data. Is that how I should be understanding this talk or the ideas here?
Yes, exactly. So fix the model, try to estimate the same parameter, but just change the mean that you use to do it.
Right. Okay, cool. The other thing, you might have mentioned this, but why n equals 2?
Okay. So the parameter n appeared in that harmonic mean, and if you just minimize it, treating it like it's a parameter, it's minimized at n equals 2.
Okay, so splitting into 2, it just happens to be better than 3 or 1.
Exactly. Yeah, it's just the function. It's a scalar. Like you just derivative and 0, and you get that.
Did you have the function on a slide?
Yeah, I did. Let me go ahead and share it again. Share Chromium tab. Let me go ahead and put it there. I gotta scroll through it. Right here. See? N and then root n. So let's just take the derivative and set it equal. So when n equals 2, this whole term goes to 0. When you subtract 1, you're only left with this.
Right. So E here is like the end point of your distribution.
Yep.
So I guess E plus is the largest eigenvalue.
Yep.
Okay. Okay, yeah, I think I get it. Of course, if anyone else has any questions, you can just pop in.
Right.
If not, just the Davis-Kahan inequality, I think maybe everyone here has already seen it already, so maybe I'm boring people, but could you give a few words about the intuition behind it? Like, I think I've seen it before, but
I see. So
better looking it up.
this one, I've forgotten the direct proof of. The intuition, so that particular one is slightly sharper than the ones that usually appear in textbooks, but let me give you the reference. This one is a useful variant of the Davis-Kahan theorem for statisticians. And it's basically, I don't know, I think if you were to Taylor expand a perturbation, maybe that's what helps, but I don't remember the proof right off the top of my head.
And finally, I think at the start you had this interesting example, and I guess it was an example, so you might not know too much about it, but you were talking about thresholding these matrices. So you pick a value, and if you're bigger than it, it's 1, and if you're smaller than it, it's 0. Do you know how they actually pick the threshold values?
That's like, there's definitely papers on optimal, like different thresholding things. I don't know sort of the asymptotics or like depending on the context. So like if they're heavy-tailed or they're slightly crazy, it takes some different considerations. But
Right.
but I know that this is a very popular topic and context dependent, I think.
Yep. Okay, thanks.
But I don't know. So in this case, like with this data set, it was like, I think there's all sorts of pre-processing that goes into it. So it's a little complicated to say, like people's heads rotate. This was the story I was told and stuff. And
Cool. Yeah, I think that's all of my questions. Thanks.
yeah, no problem. Any other questions? Okay, then. I'm still online if anybody wants to chat.
It was curious, maybe this is a very, not too smart question, but it was curious that you minimized over n, which originally was the number of patients.
Yeah, so why am I minimizing over n? So like the total aspect ratio is kept fixed the whole time, right?
Mm-hmm. Yeah.
Right. So the total number of points of the data is fixed, but like what I can choose now is capital N. At least, so I'm not sort of doing anything to keep the break independence, but I'm just saying keep 2 boxes or keep 3 boxes or keep 1 box, right? So it's not sort of super rigorous in the sense that if I did something adaptively for each finite sequence, I could maybe do better. But all I did was just split it off and sent it into 2 different bins without looking at them.
Okay. And also, okay, this is maybe not really the core of your talk, but then I saw the matrix version of the AMGM inequality. But, so it was not clear to me what was that like my less than or equal symbol. Probably is the shrinkage that you adopt.
Yeah, no. I'm so sorry, I forgot to define it. So that's the positive definite ordering. So if a matrix M1 and M2 are positive definite, M1 is less than M2 if M2 minus M1 is positive definite. Okay. So take the right-hand side, subtract it, and all the time values are positive. It's not trivial to prove. So the case for n equals 2 was in that book. And then there was some article where in some SIAM journal, linear algebra, where they generalized it. In the first case, it's just a big short complement, and then I think it just got a little bit more complicated. But I mean, part of that complication was they had a more general theorem they proved.